Okay, here we go. So I am more than glad to welcome Professor ROCH. ROCH is the chair of the Computer Science and Engineering Department in the University of Washington, St. Louis. Previously, he was with the University of Pennsylvania, and before that with IBM Watson Research. So many years, I guess, more than, if I remember well, more than 10 years. So large experience in the industry as well. ROCH was one of the first contributors to the computer engineering domain, the computer networking domain, sorry. And since then, he's worldwide renowned as one of the main contributors to this domain. I will not go forward because he has a very long CV. Just to say that he got his first degree from ENST, which was a former name of Telecom Paris. So ROCH, welcome home, and the floor is yours.
Okay, thanks Danielle for the introduction. And again, sorry not to be here in Paris. I had all intent of being there. My daughter is actually studying in Paris. Anyway, so actually what I'm going to talk about today I'll do it in a format that I'm not completely used to. I actually finished the slides literally about half an hour before the start of the talk. And it's sort of a two-part presentation that are both related, that are part of joint work that we've been doing with a colleague at Google, Henry Sarioban, and two of my PhD students, Jiaming Q and Jia. Jia is now at ByteDance. And the topic is really looking at how to improve bandwidth utilization on inter-domain links under some very specific conditions, namely when you're trying to meet delay guarantees for certain types of flows, right? And so, as I said, the target is links between data centers, and you know, basically today, if you look at most large cloud providers, sorry, I thought there was okay. If you look at all large cloud providers, they're running in some sense their own network, and actually Israel yesterday was showing us how to take advantage of that by building your own network on top of that. Now, these networks are pretty much, you know, mini internet in the sense that they use the same technologies, but they basically are operated by one particular, you know, entity, and so they have, you know, there's much more opportunities, unlike the internet where you had this distributed decision process that you know, nobody essentially could ever agree who is responsible for, you know, a problem. Here is sort of much more centralized, and so there are lots of opportunities for improving performance and optimizing things. And so one of our goals was really to try to figure out if you have traffic that has, and again, since it's a single provider, you can actually control the profile of the traffic that's entering those networks. And so if we have traffic with, you know, well understood profiles and specific guarantees that are required, how can we meet those guarantees, but at the same time do it at the lowest possible cost, where for us, cost is primarily bandwidth, right? And in doing that, you know, we looked at a couple of different knobs, right? In particular, the type of schedulers that you have in the network, and how you can actually leverage those schedulers to realize those performance guarantees. And we started with the basic component, which is what happens at a single node, and then built on top of that. And so the single node part is a pretty well, you know, it's a relatively mature piece of work. We've actually published about it several months ago, and that will be the first part of the talk. The extension to the actual network side of things is the more interesting one, and the one that is actually work in progress. And actually, the slides on that part, as I said, were pretty much hot off the press as of this morning, and they will probably self-destruct after this talk. All right. So the two parts are single node, multi-nodes. In both cases, the goal is to look at a range of different schedulers. For the multi-node case, we will actually only be able to look at the more sophisticated part, which is, you know, assuming a pretty powerful SCED, like, which is sort of an earliest deadline first base scheduler that relies on service curves. And I'll present evaluations for all the two settings. Couple of things for those of you who will essentially sort of zoom off after this, right? As I said, so a couple of takeaways if you just sort of stop listening right after I finish this slide. In the single node case, as I said, it's a pretty well understood problem. And one of the things we were interested in is if you have traffic with a certain profile, and can you actually, by changing the profile of the traffic and taking into account the fact that there's a penalty when you do that, right? That there's going to be potentially a delay associated with reprofiling the traffic, and you still get away with an overall benefit if you're trying to meet certain latency target. And in the single node case, it's a relatively, quote unquote, simple process and a relatively standard set of results and relatively well understood. It doesn't help you when you have sophisticated / optimal scheduler, but it actually can help you quite a bit when you have simpler schedulers, and I'll go over that. The multi-node case, as I said, is a more interesting one, and there is actually a trade-off. If I want to convey one thing, is maybe the intuition behind this trade-off. So if you think about a traffic profile that's coming in, and you might decide to essentially slow down how the traffic gets into the network, right, to make it nicer for the network, smoother, right? There's a cost, as I said, for that operation, that smoothing of the traffic, and it's a cost that you pay once whenever the traffic enters the network. But now you have smoother traffic to deal with inside the network. Now, because you've essentially burned up part of your delay budget in making the traffic smoother, you now have a smaller delay that you can allocate in the network. And the question is, and so that requires potentially more bandwidth. But the traffic is smoother. And so when the traffic is smoother, you can actually usually meet delay requirement with less bandwidth. And so how does that trade-off come out? That's essentially the interesting part. And it turns out that there is usually a sweet spot where by doing a little bit of reprofiling, of re-smoothing of the traffic, you let it in the network, you actually come out ahead. And I'll try to explain, how we go about exploring that question. All right, so that's the base system configuration. We're going to assume traffic profiles that are in the form of token buckets. So it's a 2-parameter. I'll do a very quick recap of the token bucket in a second. They're attached, the end hosts pump traffic into the network. The traffic sort of arrives at every node in the network. There is essentially a buffer and a multiplexer and then a scheduler that determines who goes out next on the various links. And our goal is to basically realize end-to-end guarantees for all these different flows that are going to be heterogeneous in both their profile and the performance requirement, namely the delay guarantees, and do that while minimizing the overall network bandwidth. Actually, for the network setup, the results that we have are for minimizing the total network bandwidth, but you can actually extend the work to any wide sense increasing function of network bandwidth. It could be the maximum or any kind of weighted sum. The approach just carries over without much change. So token bucket, just a very quick reminder, it's a 2-parameter sort of envelope that limits, that controls the amount of traffic a user can inject in the network. There's a burst size and there's a long-term rate. And you can generalize this, you can concatenate them, and actually we'll take advantage of that. The bottom figure is essentially showing you the concatenation of 2 token buckets, one with a burst size of 0 and a quote unquote peak rate, right? And the second one is as a finite burst size that is smaller long-term rate. And when you concatenate the 2, you get the result that is shown on the bottom figure. All right, so let's now jump into the single node case. So as I said, we now have the same setup, except that we're looking at just a single node. And so you have a whole bunch of flows. They have their own profile, right? And they have all their own deadlines, and they're arriving at a shared link with a scheduler that's going to then decide who goes out next. For simplicity, we're going to assume a fluid model, right? So you can actually extend the result for a packet type environment, but here we're going to sort of makes things simpler for us and just assume a fluid. And we're looking at what is, the smallest link speed that you need in order to meet all those deadlines for all, given all the flow profiles. And that's obviously a function of the type of scheduler that you have. Right? All right, so we're going to look at three types of scheduler: dynamic priorities, namely SCED, right? So which is essentially in an earliest deadline first, where the deadline is not just a constant, but it is given by a service curve, right? And so you look at when you arrive and you compare your arrival curve and your service curve, that gives you a deadline, and that's then fed into an earliest deadline for a scheduler. The second one is a standard static priority, and the third one is just a basic FIFO, right? All right, and as I said, one of the things that we're going to be investigating in what happens if we can actually change the flows profile, pay whatever price we need in doing that, but then sort of potentially make the flows smoother and therefore easier for the network to handle, even though there's now a tighter network delay budget that remains. And we want to understand, do we gain? How do we gain? How do we do it? And how does that change across different types of schedulers? All right. So in the case of the dynamic priority scheduler, and I don't want to sort of, there's actually, for this particular part of the work, there's a paper that documents all the different results, and so people can go and look at it if they're interested. The optimal result is essentially to use a service curve, which is just the arrival curve, the profile, right, the token bucket profile, shifted by the deadline, and feed that into a SCED a scheduler, or earliest deadline for a scheduler. And that's actually, you can prove that this is sort of the optimal. In some sense, it's a dual result of the standard well-known result that earliest deadline first maximize the schedulability region for a set of flows, right, with certain deadlines, right? And in this particular case, there's actually no benefit in actually tweaking the profile of the flows before feeding them in the scheduler. I mean, the scheduler is optimal, right? So there's not much you can do. But that's not the case for simpler schedulers. And so if you look at the static priority scheduler, there's actually there's a first question that you need to answer when you look at the static priority case, right? Which is, I have these different deadlines. How do I map deadlines into priorities? And so that's by itself is actually a non-trivial question. We don't have a completely full answer. What we know is that if you have a larger deadline, we should never map you to a strictly higher priority than a flow with a lower deadline. But there's going to be actually a few cases where flows with different deadlines should actually be in the same priority class, right? So the general result, that there's a certain implicit ordering of deadlines versus priorities, but it's not a strict ordering in the sense that you could have cases where it's actually better to put two flows with different deadlines, but put them in the same priority class, right? And the intuition is pretty obvious. It's that if you have two flows with deadlines that are pretty close to each other, it might actually not be a good thing to put them in strictly different priority classes, because you're going to penalize one over the other, even though in practice they're really very close in terms of their deadlines, right? Now, we're going to, in some sense, ignore this, and in the case of the problem that we're looking at, including the benefits of potentially reshaping the flows, we're going to map flows to deadlines, deadlines to priority in a strict order. So if you have a smaller deadlines, you get a strictly higher priority. Now, when you do that, you can actually compute what the optimal sort of capacity is. And it's basically with this, again, I'm not going to go into the specifics of the expression. The one thing I want to highlight is that it's basically the same bandwidth as what you had before, plus an additional term, which essentially captures the fact that you have, so if you have less flexibility, the deadlines now are in some sense static, as opposed to the priorities are static as opposed to dynamic. And in the worst case, you actually can show relatively easily that you can require twice as much bandwidth by using the static priorities versus the dynamic priorities of the EDF type scheduler. All right. Now the question that, as I said, I originally asked was, can we do better if we actually change the profile of the flows? And the answer is yes. And again, it's a relatively intuitive, right? If you have two flows that are sort of put into two different priorities, it's a very blunt instrument. You're not very subtle. And there's usually room for basically lowering the performance that you gave to the higher priority flow, maybe minimizing its impact on the lower priority one by reshaping it, right? Because that higher priority flow is usually going to get a much better performance, a better worst case delay than it really needs, and there's therefore some benefit that, or some spare capacity that you can leverage by essentially lowering its sort of burstiness and therefore minimizing its impact on the lower priority flows and gain from that. And so you can formulate this as an optimization problem. It's a sort of a two-step procedure. The first one involves a binary search, and the other one is assuming that you know what the optimal bandwidth is. How do you find the optimal reshaping parameters? Again, I'm not going to be going into the details of the solution. It's just that it essentially shows that you can actually compute, once you know the optimal bandwidth, you can compute by how much should I reduce the burst of the higher priority flows, and you can actually generalize that to many different priority classes. It's easier to conceptualize what happens when you have just two priority cases, but the procedure can generalize to more priorities. And so in this case, you will essentially be smoothing some of the higher priority flows, because in some sense they get a better delay than what they are requiring, and by smoothing them, you still are meeting their delay requirements, but you're minimizing the impact that they have on the lower priority flows, and so therefore you can get away with less bandwidth and meet everybody's deadlines. Now, if you get to the FIFO, then that's sort of it's a pretty bad solution in general, right? And it's relatively straightforward to compute the amount of bandwidth that you need when you have a FIFO. It's basically the worst case of all the deadlines that you have to meet. You're sort of driven by the tightest deadline. That's and assuming that flow arrives last, and then how much bandwidth do you need? And then again, in this particular case, you can benefit from reshaping. It turns out that it's the other way around, is that you're better off by reshaping the lower the flows with a larger deadline in order to minimize their impact, the impact of their burst on those flows with the tighter deadline. And it's a similar procedure as the one for the static priority, just slightly more complicated, because there are fewer constraints that help partition the problem. And so considering all the different cases becomes a little bit more unwieldy. All right, so in the case of two flows, right, again, you can get exact expression. That's what I was mentioning earlier, that you can find out how much worse is it in the worst case compared to a dynamic priority scheduler. But the main thing is what I alluded to earlier, is that in the case of static priority, what you end up doing is reshaping the higher priority flow. In our case, flow. The smallest deadline is the deadlines of flow 2. So we start, the last deadline is the smallest one. Right? DN is our smallest deadline, and D1 is our largest deadline. Right? And so again, here the intuition is that you reshape to some level, right? You reshape the highest priority flow in order to mitigate its impact on the lower priority one, and that brings you some gains. And in the case of the FIFO, it's the opposite. All right, so how do we evaluate, how meaningful or substantial those gains are, and how do they vary between schedulers, and what's the benefit, sort of shaping of reprofiling the flows with different schedulers. So we did it first using just the two flows for which we have actual explicit expressions as opposed to sort of algorithmic sort of results, and then we generalize that by way of simulations for multiple flows. Right? So let me very quickly go through the because I do want to spend time on the multi-flow case, which, as I said, is more interesting, right? So this is presenting, this is in the form of a heat map where the colors indicate the magnitude of the bandwidth increase in this particular case. This is static priority over dynamic priority. So the static priority scheduler will require more bandwidth than the dynamic priority one. And as I mentioned earlier, the savings can be up to 50%. I may have said 100% before, I'm sorry. And so the lighter colors correspond to larger benefits. So you can see that even though the worst case or the maximum benefit can be pretty high, here the scenarios that we sort of, this is a representative scenario, but it's actually, as I said, representative, and we did run a whole bunch of other configuration. The benefits are relatively small. They happen in a small region where the two deadlines are actually close to each other, and you know, that's pretty intuitive, because when the deadlines are close to each other, that's when the static priority is a very blunt instrument, since we're mapping the two flows to two different deadlines, to two different priority classes. All right. Now, this is comparing the same heat map, right? Comparing now dynamic priority, the SCED based, to a FIFO, the region where dynamic priority is better, or vice versa, FIFO is worse, is now a little bit bigger. It's in the region where basically the tightest deadline is relatively, both deadlines are relatively small. And you know, again, this is sort of a intuitive in the sense when both deadlines are relatively small, putting everything together in the same buffer and serving them FIFO is probably not a very good or very effective scheme. All right. So and now the last one is static priority with FIFO, which is sort of a relatively direct sort of consequence of the two set of heat maps that we saw. Let me see if I can find the. Well, no, I don't know if you can see. There's this little triangular region in the around the sort of the boundary, the diagonal, which is sort of a darker shade, and that actually corresponds, which is this particular the one in the middle. This is the one that actually corresponds to scenarios where putting the two flows in the same priority class would actually have been better than putting into separate classes. And that's why we actually are seeing here that a FIFO will actually outperform static priority. But otherwise, static priority does better, and it does better when the tightest deadline is relatively small and the largest one is not too large. When the largest one is not too large, you don't have a lot of, I mean, you know, that when the smallest deadline is pretty small, then this is when you expect that you'll have, by putting the two flows together, this is where you're going to have the most impact or the most difference between static priority and FIFO. All right, so this is actually looking at the benefits of shaping, right? And in the case of static priority, the benefits are primarily when the two deadlines are close to each other, because that helps us mitigate the penalty of, in some sense, putting those two flows into the separate classes. By reshaping, we actually are able to minimize, you know, the difference in treatment that the two flows occur. And in the case of FIFO, shaping will help us primarily when essentially the deadline of the flow with the longest deadline is relatively large, and the other one is relatively small, because then we have lots of room where we can reshape this other flow before putting it in this shared buffer, and in the process mitigate the impact that it has on the flow with the tightest priority. So it's a pretty intuitive set of results. All right, so the next configuration is basically a little bit more realistic. We have a whole bunch of different classes with different deadline combinations, different flow profiles, and we're running a whole bunch of different experiments. And now, instead of you know, just two flows, we have many flows that are drawn from these profiles and that are going to be multiplexed on a given link. And we again going to be looking at what are the advantages of the different schedulers over each other, and what are the benefits of reprofiling, reshaping flows before letting them into the multiplexer, right? And so the findings are sort of somewhat consistent with what we've seen, except that I think the slightly surprising thing was that, although not too surprising given what we'd already seen for the two-flow case, is that if you do actually reprofile, reshape the flows before letting them in, the benefit of a complex scheduler in the single node case becomes much less. You can actually get relatively close with both static priority and to a lesser extent FIFO. Reprofiling also helps sort of mitigate or minimize the difference between static priority and FIFO. And it depends a little bit on the distribution of the deadlines, but it actually shrinks the gap between the performance gap between the two. And FIFO is the one that actually, in some sense, benefits the most because it's the bluntest instrument. And then if you essentially reprofile the flows so that you make them as nice as possible, that's where you stand to gain the most. I'll skip over that slide, and so I want to jump into, we have about 15 minutes, the multi-node case, which, as I said, is much more interesting. Again, this is very preliminary and it's partial, and so we're going to be only looking at dynamic priority schedulers. So what we have now is this setup where we have actually a real network, not just a single node. As before, you have token bucket controlled flows that have deadlines. And what we want to do is minimize the total amount of network bandwidth that we are going to need in order to meet all those deadlines for the flows crossing the networks. The path of the flows can create cycles, right? And so there's, it's not just a tendon network or digraph. You can have cycles in the network, and we want to try to figure out how we get the minimum bandwidth for all those flows. So we're going to, as I said, use SCED, which is this EDF-based scheduler, or that relies on service curves, but we're going to limit the range of service curves we consider to essentially the service curves on the left diagram, right, which consist of a delay element, so you can delay, serving of flows by a certain amount of time, and after that, you essentially have a two-slope token bucket where you initially start at a rate, which is a high rate, and then eventually you taper off at a rate, which actually is the long-term rate of the flow itself, right? And so in the lingua of network calculus, you can sort of concatenate those two service curves, or actually three service curves, and that is what giving you that composite piecewise linear service curve that we're then going to be using as the input into our dynamic priority scheduler. Now, one thing to note is that once you are relying on SCED and dynamic priorities using these service curves, the reprofiling operation that you apply to a flow can be actually a logical one, right? So you don't have to actually delay the packets, right, or the bits, right, before you let them in the network. You just have to know that logically they now have a different deadlines, because if they arrived earlier, right, and they've been let in, they would actually have been delayed by the reprofiler before being let into the network. And so the advantage of the dynamic priority scheduler and SCED is that it allows you to operate in either a work conserving or non-work conserving mode, depending on whether you're interested in lowering the average delay, right, or the actual delay, or minimizing buffer requirements in the network. All right, so this whole thing can be formulated as an optimization, right? So the inputs are the arrival curves of the flows, the deadlines, the path, right? So we assume that the network topology and the routing is fixed. You could actually include them in the optimization, but that's potentially interesting, but sort of for another day. And the variables are, what service curve do I give each flow at every hop in the network? Now, it turns out that you can, even though we have these sort of general piecewise, three slope piecewise linear service curves at every hop, you can sort of without sort of sacrificing any optimality of the results, you can actually limit those to different delay elements at every hop, but the same quote unquote dual token bucket or piecewise linear service curve across all the hops, right? And so the optimization is then, and the constraints of the optimization are the end-to-end delay deadlines that again, you can formulate using the standard network calculus framework, right? And so the optimization is just, and here is the sum of the link bandwidth. As I said, it could be any wide sense increasing function of the link bandwidth, could be the maximum or a weighted sum. So you want to minimize this summation where the variables are how do you allocate delays to each flow on every link, and how you actually vary the reprofiling, which is these two token buckets in sequence that I was referring to, given the constraints that you need to meet the deadlines. So if you look at actually a single link, right, this is in some sense how it looks like, and I think that the figure is useful in building some intuition. So the light blue curves in dotted format are actually the service curves that you're guaranteeing every flow. And so you have first a delay element, and then you have a certain rate, high rate at which you serve the flow, and then you taper off at a lower rate, right? And here we have an example for 3 flows, and you have therefore 3 different service curves. And the dark blue line is essentially what you end up with when you aggregate, you put all these service curves together and you say, I have to meet them all. And that's basically what your link has to guarantee. And so the minimum bandwidth is essentially that red line. And what you're looking for is among all the possible red line that are above the dark blue red line, which one is the one with the smallest slope. And that's essentially determined by the inflection points where you go from increasing to decreasing in the aggregate service curve. And so you can actually, if the order of these inflection points is fixed, right, then you can actually formulate this as a nonlinear program, right, in terms of minimizing how you meet the deadlines, right? So if I give you a certain set of deadlines for each flow, right? What is the delay budget that you've allocated for that flow at that node, right? Then you can actually, and you fix the ordering of those deadlines, then this can actually be formulated as an NLP. The problem is that covering all the possible ordering is combinatorial in nature, and so you have then on top of solving that NLP for each link, you have to actually have a randomized search that allows you to cover all the different orderings. Now, we can actually do it, but we can only do it for very small topologies. And so as a result of that, we were motivated to develop a sort of a heuristic, right? And so I'll briefly describe it in a second, because I think it's sort of a somewhat interesting heuristic. It generates a whole bunch of starter solution, and then greedily it seeks to improve each one of them by leveraging essentially a notion of slack, right? And so what the greedy heuristic does, it doesn't improve things in terms of requiring less bandwidth on a given link. So it goes on a link by link basis and tries to see, can I do better on that link? Where better is not in terms of lowering the amount of bandwidth that you need on that link. You already have an optimal solution given the delay budget on that link. But better means, can I actually reprofile, makes some flows smoother without violating their local deadlines, and without obviously changing the local bandwidth, which is already the minimal bandwidth that you can get. But because I'm now making those flows smoother, that will actually benefit the other links, right, over which those flows are going to be going, right? And so this is sort of illustrating what I was just alluding to, right? And so if you look at this particular example, we have again 3 flows, right? And the red dot on the left diagram represents where the red line and the dark blue line intersect, and that's how you determine your minimum bandwidth. Now the T prime values, right, that you see are basically the deadlines for all the flows, right? So in here, right, it happens that the third flow is the one that is actually determining what the minimum link bandwidth should be. Right? But if you look at the previous deadline, right, that flow actually, in some sense, sees that there's some slack, there's some extra capacity because the bandwidth is not tight in terms of meeting that particular deadline. And so what we do is we essentially now start increasing the reprofiling, that how delay of the third flow, right? This is sort of if you look at the service curve for the third flow, which is beta 3J, right? And that's now on the right-hand side. We are actually, by increasing reprofiling, we actually sort of lowering its peak rate, or its the rate of its first token bucket, which means that it now starts contributing to the aggregate service curve earlier. And that's what is then, it is smoother, and that will actually benefit other links, not this particular link, but any other links on which flow 3 is actually going to be traversing, and you can keep doing this until you hit some boundary conditions. And so we keep doing this on every link. So the heuristic is sort of a whole bunch of different pieces, but that's actually the core component. And then we we keep applying that heuristic until we find no more improvements. So let's see how that works, right? And so the first thing that we did is we said, okay, how well does that heuristic do when we actually can come up with a quote-unquote exact solution by solving this nonlinear program, which we can only do on very, very small topologies. And so this is showing you results for tandem networks with on the top two figures using 3 flows, and we vary the number of links from 2 to 10. And so the diagrams on the left is showing you how far our greedy heuristic is from the exact solution, and it's roughly within a few percent. But the improvement in compute time, in runtime, is about 3 orders of magnitude. And then in the bottom things, we ran a tandem network of 2 links and a larger number of, flows that goes from 2 to 5, actually a smaller number of flows. And there actually the difference here is less than 0.5% on average. But the improvement in runtime is like 6 orders of magnitude, because actually the NLP is much more sensitive to the number of links, to number of flows. Number of links than number of flows. All right, so now let's see how it helps. And so we picked a sort of a network that's sort of inspired from a North American topology for inter-datacenter links. This is actually the Google. In part of the Google inter-datacenter network, and we comparing our solution to sort of 2 baseline, 2 extreme solution. One where you do no reprofiling, so you get the flows in the way they came in, and you do your best at every hop. And the other one is you basically burn up the entire delay budget by making this flow as smooth as possible before you let it in, which means that the delay budget is now 0, but remember, we are looking at a fluid environment, and so you can actually, if you allocate that rate, the rate which you use to smooth out the flow at every hop, then you essentially have a network delay of 0. We're not considering propagation or transmission delays here, right? And so, and we then looked at a whole bunch of different flow profiles that are sort of derived from sort of existing traces. We used the Facebook, actually Meta paper of SICOM 2015 that reports on a number of statistics for different flows. And so here are the results, right? And so when you do you compare yourself to the no reprofiling, you get actually improvement of the order of 40%, 40–45% across a pretty broad range of experiments. And when you compare yourself to to full reprofiling, namely full burning up of the whole delay budget in making the flow smoother, you have actually improvements of the order of 25%. And the bottom, and that's the top two figures, and the bottom figure is actually showing what kind of decisions does the greedy heuristic make in terms of deciding whether to how much to smooth or not, right? Where 100% smoothing means that you've essentially burned up your entire delay budget in making the flow smoother. 0% means you've done nothing. And we can see that there is indeed, some sweet spot. I mean, it varies as a function of the path of the flow and the profile of the flows, right? But by and large, most of the decisions are somewhere in the middle, but which sort of highlights the fact that, it is not a sort of a straightforward decision. All right, so let me wrap this up. I think we're hitting the 45 minutes mark. And so, again, I think what we've been looking at is how to essentially meet end-to-end delay deadlines on networks that we fully control. By fully controlled means we can control how we let traffic in, and we can control the routing, obviously, right? And we can control the scheduling on every link. That's obviously a very aggressive setup, right? But that's at least the one that we started with. The single hop solution is a pretty well understood. There was nothing drastically surprising, except maybe that reshaping or reprofiling flows, which in the single hop you actually are operating in a non-work concerning if you want to help schedulers such as a static priority or FIFO. I think the slightly surprising thing is that, yeah, you could actually get pretty close to the performance of of a sophisticated dynamic priority scheduler if you were able to intelligently reprofile the flows. The more interesting or more realistic or practical sort of implications are in the multi-node case, the actual network case, where I think the most interesting thing is that there is a trade-off that exists, right? And in some sense, it's because you pay this reprofiling, this reshaping price once, but then once you've paid it, you essentially benefit from it throughout the whole network. And in some cases it helps, in some other cases it doesn't. There are lots of places where we're looking at sort of extending the work, right? Obviously, is extending what we just did for the multi-hop, the multi-node case to with a dynamic priority scheduler to FIFO and static priority. The other one is to actually look back at the dual problem of the co-admission problem, namely if the bandwidth is fixed, what kind of benefits do you get in terms of, say, schedulable region if you actually do reprofiling of flows? And then there's the standard sort of question of, well, these deterministic guarantees are all good, but they're not, in many environments, they're not really, I don't care about those. What I care is the 99.99 percentile, which is a statistical performance metric. And so what happens in those scenarios is also something that I think is obviously worth looking into. And I will stop here.
Thank you, Roch. Questions?
Hello, can I ask one question?
Oh, sure.
Please. Yes, go ahead.
Yeah, sorry, my audio is acting up. Can you hear me, Roch?
Yeah, I can hear.
Yeah. This is Kumar here. So very interesting talk, and I've forgotten the details since it's about 20 years or so ago. But we were looking in the 90s at scheduling semiconductor manufacturing plants, which are huge, which have like a flow with about 200, 500 steps, and they're highly re-entrant and so on. And we designed a policy called fluctuation smoothing, which also did fantastically good performance. And I don't follow the full details of it, but I think it's interesting that the smoothing idea is useful. In our case, we were also trying to smooth flows by priorities at each step of the way, by trying to kind of make things make flows periodic and so on. I believe that MD1 or rather deterministic arrivals would make it better and so on. But anyway, maybe interesting.
Right, Yeah, that's interesting. Yeah, actually, if you can send me a link to that paper, I'd love to take a look at it.
Okay.
Indeed, actually, making the flow periodic is in some
Yeah.
sense smoothing it to the max, right? Which in some cases is the right answer, depending on your delay budget and how bursty that flow is.
Right.
That's part. Yeah.
So we actually implemented in semiconductor plants, and it actually worked well. It was implemented in an IBM plant in Burlington, Vermont, actually.
I see.
Yeah.
Send me a link. I'd love to look at that paper. Yeah.
Sure.
So I have a question about the potential use of stochastic network calculus rather than shaping curves and the classical deterministic one. Can you hear me?
Yeah, I can hear you.
Okay.
Yeah.
Yeah, so I mean, absolutely, right? So I think, as I mentioned, right, in that one of the last thing that we I think is interesting to look at is what happens when instead of deterministic guarantees, you're looking at more statistical guarantees, and stochastic network calculus would obviously be the tool of choice. It's obviously unclear, right? I mean, I believe that there'll be some benefits that are still remain when you go from a deterministic to a statistical setting. However, what I don't know is how big those benefits are as network scale in both capacity and or size, right? I mean, you have so many results that basically, are large scale laws, right, that show you that network become or links become more efficient as they get bigger and bigger and bigger. So I think I don't know, but definitely stochastic network calculus would definitely be the tool that you would want to apply to try to explore those questions.
Thank you.
Other questions? I would have one, Rob. When looking at mobile networks, radio access, the available bandwidth depends on plenty of parameters like mobility, speed, whatever, location, of course. And so different types of schedulers are used, like proportional share, in order to take this into account. So how do you feel like that these schedulers will behave in this context?
So I mean, yeah, I haven't really thought about this because, as I said, we were pretty set on an environment where we could control everything, and the mobile environment is obviously doesn't fit the bill. I think in the mobile environment, there's obviously there's the more basic question of, do deterministic guarantees even make sense, right? And in such a setting, because if you have variable bandwidth, then there might be instances where you may not be able to meet, right? So I think you would first have to be able to sort of reformulate the problem to accommodate sort of statistical guarantees, which I think you need if you're going to be dealing with a variable bandwidth links, unless you can bound the variability of the capacity. But even then, I think you may end up having to, no matter what, introduce, right? And then once you've sort of dealt with that particular problem, namely extending to statistical guarantees, then it may actually be that the amount of reshaping that you do varies dynamically itself as a function of the amount of bandwidth that you have. But yeah, these would be actually interesting questions to look at.
Thank you. No more questions? ROCH, thank you very much.
Sure.